All right, let's dive into a technique that seriously feels like a secret weapon in your coding toolkit. We're talking about the prefix sum power-up. You ever been in a technical interview, staring down a problem about summing up parts of an array, and you can just feel that clock ticking? Well, there's this incredible trick that can turn a slow, clunky loop into a calculation that's like lightning fast. This is how the pros make it look easy.
So let's just set the stage with a super common problem. Imagine you've got an array of numbers, and someone asks you to find the sum of a specific slice of it, like from the second element to the fourth. Now, how would you do it? The first thought is, okay, I'll just loop through and add them up. But what if you have to do that 1,000 times for different slices? That approach gets slow, really fast.
Well, the elegant solution to this is called a prefix sum. The idea is actually pretty simple. We just do a little bit of work up front to create a second array. And in this new array, every single element is just the running total of the original array up to that exact spot. You can think of it as pre-calculating all the possible sums that start from the very beginning. Okay, let's see this thing in action with the array 2, 4, 6, 8, 10. For our new prefix array, the first element is easy. It's just 2. Now for the second spot, we take that running total of 2 and add the next number, 4, which gives us 6. Then we take that running total, 6, and add the next number 6, which gets us to 12. And we just keep this train rolling. 12 plus 8 is 20, and finally 20 plus 10 is 30. And just like that, we've got our complete prefix sum array.
So why on earth did we do all that? Well, here's the magic. If we want the sum from index 1 to index 3, which is 4 plus 6 plus 8, we don't need a loop at all anymore. We just grab the running total at the end of our range, which is prefix 3, and then we subtract the running total of everything that came before our range started, which is conveniently stored at prefix 0. That's just 20 minus 2, which gives us 18. Instantly, no loop needed. And the difference here is honestly night and day. The brute force way needs a whole new loop for every single time you ask for a sum. It gets bogged down. But with our prefix sum array already built, any query we make is just one single subtraction. That's what we call an O1 or constant time operation. It means it takes the same tiny amount of time whether the array has 10 numbers or 10 million. It's just unbelievably efficient. Okay, so that's awesome for range sums. But the real power of this whole idea, this running total concept, comes when we start applying it to more complex problems. So let's level up and take a look at something a little bit trickier.
This right here is a classic problem from LeetCode, number 560. We get an array and a target number k, and our job is to find how many different continuous subarrays inside that main array add up to exactly k. Trying to solve this with a simple loop or even nested loops would be an absolute nightmare, way too slow.
So the trick here is to completely reframe the problem. As we go through the array, we're keeping that running total, our prefix sum, right? Let's call it x. Now, if we're looking for a subarray that sums up to k, and our total sum so far is x, then what we're really asking is this. Hey, have we at some point in the past seen a running total that was equal to x minus k? Because if we have, that means all the numbers between that old point and our current point must add up to k. That's the big idea.
And to answer that question, have we seen this before? We need a power-up. We need a way to instantly remember all the prefix sums we've calculated so far, and maybe even how many times we've seen them. And this is the perfect job for a hash map. It's going to act like our memory, our history book, telling us in a split second if we've seen that x minus k value before. Okay, theory is great, but let's make this real. Let's do a quick dry run. Our array is 1, 2, 3, and the target sum k we're hunting for is 3. We'll start with a running sum of 0, and, this is important, a map that's initialized with 0, 1. This little trick helps us catch any subarrays that start right from the beginning of the array.
All right, let's kick things off with the very first number, which is 1.
So our running total, our prefix sum, is now 1. And now we ask our big question. Does our map have a key for prefix sum minus k? Well, that's 1 minus 3, which is negative 2. We take a quick look at our map, and nope, no negative 2 in there. So no subarray found yet. All we do is update our map to remember that we've now seen a prefix sum of 1, and we move on.
Okay, next up is the number 2.
We take our old running total of 1, we add 2 to it, and our new prefix sum is 3.
And here we go, time for the crucial question again. We're looking for prefix sum minus k. That's 3 minus 3, which is 0. So we check our map. Have we ever seen a prefix sum of 0 before?
Yes, we have. Remember how we put it in there right at the start? That's a match. We just found our first subarray.
the 1 right from the beginning, 1, 2. So we bump our counter up to 1, and then we update the map with our current sum of 3.
Awesome. Let's process the last number in our array, which is 3. Our running total was 3, we add 3 more, and our final prefix sum is 6.
One last time, let's ask the question. We're looking for prefix sum minus k, which is 6 minus 3, and that's 3. Let's look back in our map's history. Have we ever seen a running total of 3 before?
We sure have. We just put it there in the last step. That's another match. This find corresponds to the subarray that is just 3 by itself. So we increment our count again, this time to 2, and we're done. The 2 subarrays are 1, 2, and 3. Pretty cool, right?
So let's step back. Why does mastering this pattern matter so much? Because it takes what would be a brute force O(n)² nightmare, a solution that just chokes as the input gets bigger, and it turns it into this sleek, efficient, single-pass O(n) solution that just flies. This exact pattern is a cornerstone for a huge class of problems you'll see in coding interviews. At its heart, it's all about one simple idea. Don't redo work you've already done.
And that really brings us to the big takeaway. We used a map to store a history of sums we'd seen, but this idea is so much bigger than just that. So I'll leave you with this question to think about. What other kinds of historical data could you store to look back on to help you solve future problems even faster? That's the power of thinking with history. Happy coding!